Hello, in this problem we're going to go over how a charged particle is influenced by both a electric field and a gravitational field. Let's begin. So we should see a scenario where we have an electron or a negatively charged object and it's being suspended between two electrically charged plates. Alright, so let's begin. Now, this is a very generic type of problem. In fact, this problem was the basis of the milk and oil drop experiment, where Millikan, he dropped charged droplets of oil and he was able to suspend them between two charged plates. So, like all problems, let's first start off with a sketch model of what's going on here. Okay. So if you take a look, I have a charged plate up there and I have a charged plate down here. Now, at this moment, I'm not going to draw the field lines for the electric field, simply because we don't really know what it is until we dive a little bit further. Okay, but we do know that the top plate is charged and the bottom plate is oppositely charged. Next I'm going to do is I'm going to place a negatively charged object right in the middle. Let's make it suspended. Okay, so there's my negatively charged object, and we just call that the electron. All right, and here's the other thing that we know. We do know that this charged object is under the influence of the gravitational field. Okay, so right there, what I'm going to do is I'm going to put a little pause on this model. I'm going to go to a different model over on the right-hand side. And this model will be the free body diagram model. So here we have a negatively charged object, and we know that the force of gravity is pulling on it downwards. So we're going to call that F of G. Now, if it's being suspended mid-air, that means there has to be another force that is counteracting that force of gravity pointing down. And we're going to call that the electric force pointing up. Alright, now at this point, we have to keep in mind the big concepts for this unit. Okay, so if this is a negatively charged object or a electron, in order for this electron to be pushed upwards, we need to have a negative influence towards the bottom. So towards the bottom here, this should all be negative. And up at the top, we want it to be attracted or being pulled upwards. So we're going to have a positive influence up there. Okay, so what this shows us is that the lower or the bottom negative influence will push this negatively charged object up, and up here at the top area we have a positive area, and that positive area will pull the charge up. Okay, and the force of gravity will of course pull it down. Okay, so now that we have that model there, we can continue with the original model that we started off with. So this is what we know. We know that the top plate is positively charged and the bottom plate is negatively charged. So what I want to do now is I want to create the E field for this model. Okay, and remember, the E field always comes from the positive into the negative. Okay, so I'm just going to draw some E field lines this way. Alright, and the other thing that we know is that we are also under the influence of a gravitational field. Now, the gravitational field is always in the downward direction. Okay, so I'm going to do this in a different color and also in red. Alright, so this is what the field model looks like for this problem here. Now, we're not quite sure what we're really solving for because the problem doesn't designate that, and so I did that on purpose. And the reason for that is I just want to show you how to really set up this problem so that we can see exactly what happens in any sort of given situation, where all we have to do after that point, after creating our models, is plugging in our numbers. Alright, so with these two models there, let's come up with the net force equation model, where we have the net force, which is equal to ma. Okay, F equals ma, that is just Newton's second law, and that will be all the forces that we have in our free body diagram model. So we know that we have an electric force pushing upwards, so Fe, and we also have the force of gravity pulling downwards, Fg. Okay, so after we have this net force equation there, the only thing really left for us to do is to substitute in our electric force equation and our force of gravity equation. Okay, so we have ma equals, the electric force equation is going to be there is the KQ over r squared minus mg, so that's Coulomb's law. And we also have the other version where it's ma is equal to Fe is equal to EQ minus mg. Okay, so both of these are the same equation, where the middle one, or this equation there, that simply tells us if we were under the influence of two charges, but this one tells us if we have a single charge, and that charge will be Q, that is under the or within a E field that we see here for E. Alright, so with these two models, the next step that we have to come across is the big conceptual ideas. Alright, so if this object is floating, it's just being suspended mid-air, that means that our acceleration is going to be 0 meters per second squared. Now, this doesn't mean that it's not moving. Remember, acceleration is the change in velocity. Okay, so if this object, or if this charged object is being suspended mid-air, it's at rest, and after a long period of time, it'll still be at rest, and so there is no change in velocity. Okay, well, change of velocity over change in time is the acceleration, or we can also write that as dv dt is equal to a, right? And because there is no change in velocity, our acceleration is 0. Now, the reason why this is so important is because it makes our math really simple. Now, I'm going to go with this this second net force equation because that is pertinent to our scenario. We can say our acceleration is equal to 0, which is equal to EQ minus mg, where that m is the mass of the charged particle, and in this scenario it will be the mass of the electron. Alright, now with that 0 there, it really does clean up our math a lot, where all we have to do is we can add mg to both sides, so we get mg is equal to EQ. Okay, now from here we can rearrange this formula in many different ways to actually solve for what we're looking for. So a question could be, what is the strength of this E field in order to make this electron suspended? Okay, and at that point we would just rearrange the variables, so we get E is equal to mg over Q. Okay, or it could ask us what is the charge for that negatively charged object given the electric field, and we can also go on from that direction. Alright, so what I want to do at the very end is, of course, have a little statement on what we just found out. Okay, this really does help us out with our FRQs. So I can say, in order for the negatively charged particle to be suspended between two plates, we need to make sure that the weight of the particle is equal to the electric force felt by the particle. Both forces are in opposite directions, and this allows us to have a net force equal to 0 newtons. Alright, so that's just a simple statement that really summarizes what we have. It encapsulates everything that we just solved for. And, my friends, that is how you can solve for a particle that is being suspended between two plates with the two fields, the gravitational field and the E field, being along the same axis. I'll see you next time, where we will make one of the fields be horizontal. Till then, bye-bye.